So first things first, I really would like to thank the organizers for inviting me to speak here. And I have to shamefully admit that this is my very first time at CERN, which is like, I've been to Marseille as a tourist, but I've actually never been here, which is, to me, is just amazing, actually, right? So I'm just delighted to be here. I should next mention that this is joint work with Sarah Arpin, who's actually here, right there, and a very gifted undergraduate student, Taha Hedayat, whom I was fortunate to recruit for some summer research in Calgary a couple of years ago, and so he worked on this 2 summers. And it was really nice because he wanted to learn some computing and he wanted to learn some number theory, and he had just taken a graph theory course, and so this was actually quite perfect. So this work is actually, there's an archive preprint, and it has been conditionally accepted at this year's LUCANT meeting in Providence, Rhode Island in early July, and the plan is for Taha to actually present this. And conditionally accepted means we're still like busy doing some revisions, which hopefully we'll finish while we're here. Okay, right. So, why should we care about supersingular elliptic curve isogeny graphs? Well, I can tell you why I care. I care because they have really interesting mathematical properties. So they're an object that kind of sit at the interface of graph theory and number theory. To me, this is actually very, very appealing. But there's another reason, and that is cryptographers care about them. Because they form the basis of a number of hopefully quantum-resistant cryptographic systems. I've mentioned a few here, so there's probably people in this room who have worked on variants and related systems of one type or another, and if I'm not mentioning you here by name, please forgive me. I also have some papers on this, and I'm not mentioning myself, so you're hopefully in good company. So I mean, the first one essentially was the Charles Gorin-Lauder hash function, which used these isogeny graphs to develop a secure hash function. The next reference here is the ski sign crypto system and its variants, and the last one is the scallop crypto system, and the family, and etc. sort of refers to all the variants that various people have done from this. So, so what happens is when people analyze the security of these cryptographic systems, they oftentimes make sort of assumption that these isogeny graphs behave like random graphs, whatever that means, right? But you have to, if you want to do a good security analysis, you have to make these assumptions. And now, of course, if you find certain hidden structures or patterns or something in these graphs, then maybe they're not so random, and these could kind of serve as attack vectors on these cryptographic systems. And so I think it's important to really understand structural and other properties of these graphs to see if this is a safe assumption and a justified assumption, or if there's maybe structure in there that could be exploited by bad guys. So that's another reason to care about these things. And our work in this herein analyzes some of the structure of supersingular elliptic curve isogeny graphs, and then also a certain subgraph, namely the subgraph that's induced by all the vertices who are defined over Fp. So the base field of the that we're starting with. And these vertices are called the spine. We'll say in a minute why is it called the spine. All right, so just informally, what's a supersingular isogeny graph? Well, I mean, I imagine everybody here knows what an elliptic curve is, and everybody here knows what a supersingular elliptic curve is. And so roughly speaking, what you do is you start with the prime p. That's going to be so all the elliptic curves are going to be defined over some extension of Fp. You should think of p as big. And then there's a second prime L, which you should think of as small, like 2 or 3. And so then you define a graph, and the vertices are the isomorphism classes of supersingular elliptic curves. You can also do this with ordinary curves, but we will only focus on the supersingular ones. And they are represented by the J invariants of these curves. And the edges are L isogenies between these curves, more or less. So that's the graph. That's roughly the graph. Here's an example. This is the, here L equals 2 and P equals 523. And so this is the 2 isogeny graph over F523 bar. So you see these are kind of messy objects. They have, for example, there's some, let me see if I can point this here. Right here, there's a loop, for example. There's some loops here. You also see that the edges are oftentimes somehow in pairs, right? For an edge going in the one direction here, there's an edge going in the other direction. And that's arises from the dual of the isogeny, right? So when you have an L isogeny, its dual goes in the other direction and is also of degree L. So this is what they look like, right? Okay, and what's the connection to cryptography? Well, in cryptography, oftentimes the security of your system resides in some sort of problem that's presumably computationally intractable. Like everybody knows, like for RSA, it's like factoring, and for traditional elliptic curve system, it's elliptic curve discrete logarithm, and so on. And here it's the so-called supersingular L isogeny path finding problems. And it goes as follows. So you have two elliptic curves, E and E prime, and then you're trying to find a path of L isogeny between them. So you hop from one, you start at the curve, you hop to the next one via an L isogeny, and the next one via another L isogeny until you arrive at your target curve. And that really corresponds to a directed path in this supersingular L isogeny graph. So this is a path in the graph theoretic sense. And that is presumably intractable. Many people have worked on this and found algorithms, classical ones and quantum ones. I'm not going to say anything about this because that's not the topic of this lecture, but anyway, that's the problem. And as I said, this is the intractability of this problem is the basis for the security of the aforementioned cryptographic systems that I mentioned on the previous slide. In practice, in fact, oftentimes the curves E and E prime are actually defined over FP, so their path starts and ends with a curve over FP. So does that maybe have some implications to security, right? These are the kind of questions. And so this sort of motivated us to investigate, structural, like graph theoretic structural properties of these supersingular isogeny graphs and its spine, meaning the FP vertices. So hopefully that is sort of enough convincing enough motivation to convince you that this is a worthwhile thing to look at. So I want to say something a little bit about elliptic curves and the kind of things that you run into when you study this structure. So it's a well-known fact that when you're just dealing with supersingular elliptic curve, then every isomorphism classes has a representative that's defined over FP squared. So you can always find up to isomorphism a model that's defined over FP squared. So you don't have to go to like some huge extension. And some are even defined over FP. And the isogenies, it's the same thing, right? So every isogeny is defined over FP squared, and some are defined over FP. And that's going to come in very importantly in our study of these objects. And so in particular, you might have curves that are defined over FP, and they're isomorphic over FP squared, but not over FP. But then when you go from FP isomorphisms of FP, the isogeny is defined over FP, to isogenies defined over FP squared, all of a sudden they become isomorphic. And so an example is quadratic twists, right? So if you have a, that's it. If you have an element t such that t squared is in FP, and you look at these two elliptic curves, so this is an elliptic curve and it's quadratic twist, and they're isomorphic via this isomorphism here. xy gets sent to t squared x and t squared y. And so they're isomorphic clearly over FP squared, right? But they're not necessarily isomorphic over FP, but they are isomorphic over FP if and only if T actually belongs to FP. And so here it really depends on what kind of isomorphism classes you're talking about, and then also what kind of isogenies you're talking about. So we have to be very clear here, are we talking about FP isomorphism classes or FP bar isomorphism classes of both elliptic curves and also of isogenies? Okay. So with that, let's define three graphs. This is going to be a bit of a crowded slide, but I wanted to put it all on one slide so we have it all together. So as I said before, you have a big prime P, you have a small prime L that's different, and then you can define what we sometimes refer to as the full supersingular isogeny graph. So as I said before, the vertices are just isomorphism classes of supersingular elliptic curves. Now we know that they're all defined over FP squared. Okay, and then the edges are L isogenies over FP bar. And there's a little footnote here, up to post-composition by an automorphism, right? We know that certain elliptic curves, the ones that have J invariant 0 and 1728, they have extra automorphism. And you're allowed to post-compose an isogeny with one of those automorphisms, and it's considered sort of the same thing, right? Because we're really only interested in kernels of isogenies, and of course, it makes no difference to the kernel here, right? So, so when I said the edges are L isogenies, it's a little bit of a lie. It's only up to post-composition by an automorphism, but yeah, that's a little technical detail. And now, what is the spine? So the spine is the subgraph that is induced by all the vertices whose J invariants belong to Fp. Okay, so this is a subgraph. So the vertices are still Fp bar isomorphism classes, but they are represented by all the J invariants that are now in Fp. So all the ones from Fp squared we don't consider, and then the edges are L isogenies between these vertices. So that's clearly a subgraph. Okay, that's the subgraph induced by the vertices belonging to Fp. And then we have a third graph, which we refer to as the restricted supersingular isogeny graph, which is most definitely not a subgraph. And that is where you consider everything just over Fp. So the vertices are now Fp isomorphism classes. So in particular, J invariants are no longer, like the vertices no longer have distinct J invariants, because you could have a J invariant, its quadratic twist. So J invariants might appear twice. And the edges are now Fp isomorphism classes, okay? And the spine is you can think of the spine as sort of a way to embed this Fp graph, this restricted graph, into the full graph. It's not really a subgraph, but you can turn it into the spine, and then it is a subgraph. And the reason why it was, I mean, this is terminology that is not due to us. It's terminology from a previous paper by Sarah Arpin and various other people. And you can think of the reason why it's sort of the spine is you can think of it as the vertices that are left fixed by Frobenius, and then all the other vertices sort of come off of this. And so it's like the backbone of the graph, so to speak. So this is why it's called the spine. So those are the three graphs that we look at: the full graph, the spine, and this restricted graph. All right. So here's an example. I took this from a talk by Sotakova from 2019. I stole these two pictures. So on the left, you have this messy thing is the 2 isogeny graph over F1103 bar, and this is just a subgraph of the correct expected size of the spine. Indicated by these blue vertices. On the right is the actual 2 spine of this graph. Now, I mean, where these vertices are clustered is, of course, just a function of how you draw the graph. So you shouldn't really pay attention to the fact that they're all sort of at the top there. But the difference is, I mean, the connectivity sort of looks different. If you look carefully, they have some sort of subtle differences. So for example, I mean, this guy here has a loop here, right? And he has a loop here, and this guy doesn't have a loop. Right? So the question is, is the spine really sort of a random thing in there, or is it located in a particular way? How is it connected to the rest of the graph? These are the kind of questions that we were interested in. And so let me highlight the main differences between the small Fp graph and the spine. So what happens when you move from the Fp graph into the spine to try and embed it into the big graph? Well, the first thing is that the spine has only half as many vertices as the Fp graph, because, of course, J invariants of an elliptic curve and its twist, they now get merged to one vertex. So any 2 vertices get merged to one vertex. So the number of vertices halves, right? And what about edges? Well, of course, there might be a whole bunch of elliptic curves that are not L isogenous over Fp, but there are L isogenous over Fp bar, and so you introduce a whole bunch of new edges. So that's sort of the difference. The number of vertices shrinks to half, but you introduce a whole bunch of new edges. Okay? And so what do we know about these graphs? Well, the structure of the big graph has been well studied for a long time. It's well known. We'll get to that in a minute. The structure of the small graph is also well understood. We'll get to that in a minute. The structure of the spine, not so much. That's much more recent. And so the questions that we wanted to ask is things like, how exactly are these graphs related? What exactly happens when you embed the Fp graph into the big graph in order to make it the spine? What happens to the isomorphism classes? What happens to the isogeny? So we're going to answer this in this talk for L equals 2. We also did this for L equals 3, but I'll just talk about L equals 2 because that's the most interesting case. And then also we looked at some sort of connectivity properties of the big graph and the spine inside it. And I'll also say something about L equals 2 for this. So that's sort of what we started looking at. Okay, good. Right. So the first thing is the structure of the big full L isogeny graph. This was very, very well analyzed by David Coel in his thesis. David is also here in the back there. He actually investigated this for the entire FP isogeny graph, including the many, many ordinary elliptic curves. But we will just focus here on the supersingular one. So it's a very sort of disconnected graph. The ordinary components have a very regular structure. Some of you might have heard the terminology volcano. They're all volcanoes. They look very, very nice. And then there's one component that contains all the supersingular elliptic curves, and that's the one component that we will hone into. So we're only looking at that component. It's a connected graph. It has roughly p over 12 vertices. And it's what's called an optimal expander graph. So in essence, this means that when you start walking around in the graph, pretty quickly you look like you're like indistinguishable from a random path. So cryptographers love these expanders, computer scientists love these expanders. There's like a whole study of expander graphs and their expansion properties in that graph theorists and computer scientists do. Every vertex in this graph, so it's a directed graph, and every vertex has out degree L plus 1. So there's L plus 1 edges emanating from every vertex. And that basically corresponds to the, right? I mean, the L torsion is Z mod LZ times Z mod LZ, and that has L plus 1 subgroups of order L. And that's the kernels of these isogenies. Every vertex has in degree L plus 1, except in around 0 and 1728, where the in degree is a bit smaller because of these extra automorphisms. But it's only in the neighborhood there that it's a little bit problematic. And then sometimes you might have seen the undirected version of this. If you identify elliptic curves with their duals, then you can make this into an undirected graph. And that undirected graph is almost L plus 1 regular, so almost every vertex is incident with L plus 1 edges, except in the neighborhood of 0 and 1728. So that's what this looks like. Now, what about the FP graph, the tiny one, the one that only consists of FP vertices and FP isogenies? This was investigated in quite some detail structurally by Delfs and Galbraith in a paper from 2013. And I'll separate this into two cases, the case where L is bigger than 2 and the case where L equals 2. The L equals 2 case is by far the most interesting one. Like once you get into the odd primes, it's really not that interesting anymore. The structure is really not that exciting. So, and I'm going to identify two vertices, two types of vertices. We'll call them type 1 and type 2. The first ones have endomorphism ring this order here. I'm hitting the wrong button. This order here. The second, and this is only for p congruent to 3 mod 4. The second type have this order. So when p is congruent to 1 modulo 4, then this is the maximal order of the quadratic field q adjoint square root of minus p. When p is 3 mod 4, this is the maximal order, and this is an index 2 suborder. And so sometimes you might have heard the terminology like floors and ceilings of volcanoes, or floors and surfaces of volcanoes. I'm just going to call them type 1 and type 2 vertices. All right? And normally supersingular isogenies have an endomorphism ring that's isomorphic to a quaternion algebra, to a maximal order in a quaternion algebra, right? A 4-dimensional object. But when they're over FP, they actually have a quadratic order as endomorphism ring. And it's one of these two quadratic orders. All right? So they all have Cm by one of those orders. And this graph for L bigger than 2 is not so interesting. If L is inert or ramified in this field, well, it's just a bunch of isolated vertices, so it's not so interesting. If L splits in K and P is 1 mod 4, then the number of vertices is the class number of this field, and they're all of type 2, and they form a cycle. And cycles can be degenerate, could be just one vertex or something, right? But so it's just one cycle. And in the other case, when L splits and P is 3 mod 4, it's just 2 cycles. And they both have the same length. One only is type 1 vertices, the other one is only type 2 vertices. So it's not so interesting. It's either a bunch of isolated vertices or 1 cycle or 2 cycles of the same length. Now for L equals 2, things get a lot more interesting. So when P is congruent to 1 mod 4, then you have class number many vertices. They're all of type 2, and they form a collection of edges. So it's just a bunch of edges. That's not so interesting. When P is 3 mod 8, it gets a little bit more interesting. You have HK vertices of type 1, so the endomorphism ring is the maximal order, and 3 times as many vertices of type 2, and they are connected 3 to 1, And they give these little, so the graph theorists call them claws, right? There's basically something like this, you know. You have a vertex down here where my hand is, and then you have 3 vertices where my fingers are. We call them tripods because we wanted to sort of orient them, right? Because really the 3 vertices are at the bottom, right? They're the non-maximal order, and the 1 vertex is at the top, so we call them tripods. And then when P is 7 mod 8, then you have hk many vertices of type 1. They form a cycle, and then each of those vertices in the cycle has an edge hanging off of it, joining it to a type 2 vertex. So visually, this is what it looks like. So for P is 1 mod 4, it's just a bunch of edges, so it's not so interesting. For P is 3 mod 4, you have these tripods. And for P is 7 mod 8, for P is 3 mod 8, you have the tripods. And for 7 mod 8, you have a cycle, and each cycle has like 1 edge hanging off of it. So it's a little bit more of an interesting structure, especially in the case P equals 7 mod 8. That's kind of the hard part. So now we have the structure of the big graph. We have the structure of the FP graph. So the third thing we have to look at is the spine. Okay, so here's what happens when you map the FP graph into the big graph to make it the spine. Okay, so again, what we do is you go from isomorphism classes and L isogenies defined over FP to isomorphism classes and L isogenies defined over FP squared. And as I said before, pairs of vertices in the small graph now get identified because the quadratic twist J invariants merge to be 1 vertex. Isogenies that are defined over FP squared but not defined over FP introduce new edges. And in particular, you might have disconnected components in the FP graph, and they might now be somehow joined by an edge, and they might become connected. And I should mention that a lot of this work was done by Sarah Arpin and a number of co-authors, Camacho Navarro, Lauder, Lim, Nelson, Scholl, and Sotakova, in a 2023 paper that has the wonderfully facetious title, Adventures in Supersingular Land. And they investigated this behavior of what can happen and how this embedding, this mapping of the FP graph into the FP graph happens. They investigated this in considerable detail, and they identified 4 behaviors that can happen, and they referred to this as stacking, folding, vertex attachment, and edge attachment. And rather than telling you exactly how that works, a picture is worth 1,000 words, so let me show you in pictures how that actually works. So this is stacking. You have here 2 tripods, and when this superscript T means quadratic twist. So they're the same J invariants, but in the FP graph they correspond to quadratic twists. So here J1 is attached to is adjacent to these 2 J invariants, and J1T is adjacent to their twists. And when you map into the big graph, then they just get sort of superimposed. That's the stacking. One gets stacked on top of the other one. So they go from 2 tripods into one of these. That's the stacking. Folding arises from edges sort of between 2 quadratic twist J invariants. So in the FP graph, these are the same J invariants. One corresponds to a curve, the other one to its twist, but they're now L isogenous over FP. And so here, of course, the vertices now merge. This is kind of sluggish, so sorry, and become 1 vertex, and that edge becomes a loop. So they sort of fold onto each other, right? And then attachment by a vertex. So here are 2 little cycles. You see here some of the J invariants are, well, some of them are common, but they correspond to twists. So for example, here's J1 and here's J1 twist. J1 is adjacent to J2 and its twist, and then there's another one, J3 and its twist here. The twist of J1 is adjacent to J4 and its twist, and J5 of its twist. And so what happens? So that they get attached at vertex J1, because these get identified. Then this adjacency to J2, right, those also get mapped to each other. So these 2 edges become 1. That's over here. And then the adjacency to J3 and its twist also becomes 1 vertex and 1 edge. That's over here. And the L isogeny between J3 and its twist becomes this loop. And then the same thing on the other side. Right? So J1 is adjacent to J4 and its twist. That becomes now 1 edge and 1 vertex. The edge to J5 and its twist becomes 1 edge, and the edge between J5 and its twist becomes this loop. So here now we have 2 components, and they get vertex attached at J1, and they become 1 connected component. So that's attachment at a vertex, and finally we have attachment at an edge. So here's again two tripods. It's all completely different J invariants, and somehow mapping from FP into FP bar introduces this new edge between J3 and J6, and so you have this new double edge here. So I didn't draw any arrows here, so I sort of drew them as undirected edges, but right, I mean, these edges go down if you wish, and here one goes in one direction, one in the other one. So that's edge attachment. So they really classified so Sarah and her co-authors classified in very great detail when this happens, how this happened, what happens with different components, and so on. And what we did in our work with Taha is to classify this according to congruence conditions on P. So you fix an L, and then you fix a P, and you want to know what happens, and you just stare at the P, and you check its congruence class, in this case modulo 120 when it's L equals 2, and then you know exactly what happens, how this thing maps into it, what the spine looks like. So we made this all very, very explicit. This is the first half of our theorem. This is the case P congruent to 1 modulo 4. I'm assuming that P is at least 17. For the small primes, you can just draw these things. I mean, it's small enough that you can just sort of figure out by hand what they look like. And so when you transition from the FP graph into the big FP bar graph to become the spine, here's what happens. So I mean, P equals 29 is a little bit special. So you have one component. It contains both occurrences of the J invariant 8000. That component folds. The graph has one other component, and that edge attaches to the first folded one. And then the next set of congruences is, again, you have a component containing 8000 and its twist. It folds, all the other components stack, and two of the stacked components edge attach. So you see this is all very, very explicitly described. The next one, all the components stacked, there's no edge attachment. The next set of congruences, again, the component containing 8000 folds, all the other components stacked, no edge attachment. And finally, the last set of congruence conditions, all the components stacked, no edge attachment. So literally, you take your prime, you stare, you check which congruence class it is in, and then you know exactly what happens. The version for P congruent to 3 mod 4 is a little bit more complicated, but again, it's described very, very explicitly. I want to draw your attention to these two nasty congruence values modulo 120. These are the only ones where you're unable to completely resolve what happens. So here it introduces a new double edge into the spine. That double edge is incident with two type 2 vertices, but you don't know whether that leads to an edge attachment or not. So you don't know whether it joins two components or not. And you really can't tell in this case. So we have examples. So I'll give you examples for both behaviors in a minute. But the second thing I want to show you is what the spine looks like in each of these cases. So here's P equals 5, not very interesting, P equals 29, et cetera, et cetera. So here's this is what the spine looks like for these congruence classes. So it's a vertex, this path of length 3, a bunch of edges. Here it goes on. The P congruent to 1 mod 4 case is not so interesting because remember the FP graph is not so interesting, it's just a bunch of edges, okay? P congruent to 3 mod 4 gets a little bit more interesting. The 3 mod 8 case, remember that was the tripod case. You have a bunch of tripods. So you see the tripods in here, right? Here, for example, here's a tripod that inherits an edge. Here's two tripods that get attached to this edge. The other ones get left alone. Here you keep a bunch of tripods. You introduce a new edge, etc. Now we get to the 7 mod 8. That's the interesting case. Because there, remember, you had the FP graph was a cycle. And each vertex has an edge hanging off of it. And so here things can happen. And this is the case where you don't exactly know what happens. What you know is there's an edge introduced, but you don't know whether that edge actually starts joining two of these cycles. You know the edges between type 2 vertices, but you don't know if it occurs between two connected components or inside one of two connected components. So that's the only thing that where you don't really exactly know what the spine looks like. So let me give you two examples. So this is the case P equals 71, and here you have no edge attachment. The 2 graph of F71 looks like this. So it's this cycle with these things hanging off. And so you see here, for example, here's 24 and its twist, they get identified to 1, etc., etc. So you have, this is what the spine looks like, and because it's only one component, of course there's no edge attachment, right? Because it's only one component. But here is a case, P equals 1319, which is also, I think, 71 modulo 120. And here you do have edge attachment. So here, the FP graph, has 5 components that all look like this. I only drew one of them. They all look like this, a cycle again with these vertices hanging off. And so you see here, when you go into the spine, via this guy here, there's edge attachment of 2 of these cycles. And then there's like another component here. So you really don't know whether there's edge attachment or not. So it's a bummer. I mean, that's the one case we can't really completely describe. So that's the spine. So that's the L equals 2 case, which is the most interesting one because the FP graph has the most interesting structure. Let me just tell you, we also did this for L equals 3, where it's a little bit easier because the structure of the FP graph is easier. Here you can divvy it up into 3 cases according to whether there's no folding or 1 component folds or 2 component folds. The congruence classes here are modulo 840, so there's like a big laundry list of what happens for each of these congruence classes modulo 840. I'm going to spare you the details. If you're interested, look up the preprint where it's all spelled out in detail. Yeah, so that's the L equals 3 case. So that's the spine and the relationship sort of between the FP graph and the FP bar graph. I want to address a few of the ingredients that go into, I'm not going to prove any of this, but I kind of want to tell you the kind of tools that we use. The first tool is the modular polynomial. So for your favorite L, you go to Drew Sutherland's wonderful website and you look up the Lth modular polynomial. And what does it tell you? It tells a bivariate polynomial with coefficients in the integers. And if you stick in 2 J invariants for the 2 variables, then you get 0 if and only if these 2 J invariants are L isogenous. And this works over finite fields and globally, so this is all the same. So this is great. And by the way, it works for both ordinary and supersingular J invariants. So that governs basically L isogenies. The properties is, for example, if you have a loop edge, right, then you stick in J for both variables, you get 0. And for a double edge, so this also tells you about edge multiplicities. So how do you get multiplicities of roots? Well, I mean, you do derivatives, right? This is like calculus 1 or something, right? Except, of course, here we have bivariate polynomials, so you have to be a little bit careful about what you mean by derivatives. And what it is you view this polynomial here as you take the derivative with respect to y, and then rather than taking the GCD of a derivative with a polynomial, which is what you do in order to ascertain multiplicities for univariate polynomials, you take the resultant. And then you get a polynomial in X, and that detects double edges. And if you want triple edges and higher edges, then you take higher derivatives. Okay? So that tells you sort of multiplicity of edges, and it tells you adjacencies, it tells you loops, and so on, right? Then we also use Hilbert class polynomials, sometimes also referred to as ring class polynomials. Sometimes people only use the term Hilbert class polynomial when you're referring to the maximal order of a field, but if you don't like Hilbert class polynomial, just call them ring class polynomial. So as I mentioned before, when you have FP vertices, or for that matter, ordinary elliptic curves, right? The endomorphism ring is a quadratic order. Let's call that quadratic order OD, where D is its discriminant, a negative integer, fundamental, well, it doesn't have to be fundamental. And then the ring class or Hilbert class polynomial governs which elliptic curves have Cm by that order. So you stick in a J invariant and you get 0 if and only if that corresponding elliptic curve has Cm by that endomorphism ring. So we need that as well. And in particular, these polynomials, modular polynomials, if you set the 2 variables equal and this resultant polynomial, they factor into Hilbert class polynomials. And then what it tells you also, it detects the supersingular J invariants. And in particular, a J invariant is supersingular if P does not split in this particular field or in this particular order. So you see that these polynomials govern a lot of the sort of structural behaviors of these graphs. And so here's an example for L equals 2. What do? You look up the second modular polynomial, and you see already, even though that's the smallest case, it's a nasty beast, right? It has like big coefficients. These things have enormous coefficients, which we don't really care about so much because we look at the modulo P. So this is, and then this is your, so if you plug in y equals x, then it factors into these factors. And so that tells you that you're going to have two loops at J invariant 3375 and one loop each at 738 and 8000. Of course, you don't know if these are ordinary supersingular. This res polynomial factors into these Hilbert class polynomials. So you see here 1728 is in common with these here, and this one is in common. And so you're going to have double edges between some of these J invariants and also the roots of this H15, which you can just calculate via the simple quadratic formulas. And then basically what you do if you want to understand this, so for example for L equals 2, and again this was described in considerable detail in this supersingular land paper and just translated into congruence conditions in this work. So here are sort of the ingredients that go in there, right? I mean, you consider the roots of the modular polynomial, phi2 of xx modulo p, and then the roots of this corresponding res2 polynomial, so that tells you like loops and multi-edges and stuff like that. Sometimes you may need to do the odd explicit isogeny computation because you need to figure out whether an isogeny is defined over fp or over fp squared, okay? You need to ascertain whether 0 and 1728 are supersingular. They are well-known congruence conditions for this. 0 is supersingular if p is congruent to 2 mod 3. 1728 is supersingular if p is congruent to 3 mod 4. And then you need to figure out the roots. In this case, the roots of this h minus 15 polynomial. And you need to check if they're supersingular. So you need to make sure that they either ramify or are inert in the corresponding quadratic field corresponding to square root of minus 15. Now, for the small primes, I mean, you might have some ramification there. We ruled these out. We treated these separately. Remember, I had an assumption that the primes are at least 17. And it turns out all of these are inert in this field. And so these are all supersingular. All right. And so the first three, they sort of govern the behavior of how this FP graph maps into the FP bar graph, and then the last three impose sort of additional congruence condition. And when you put this all together, you get this mass of congruence conditions that you've seen in the theorem. So this is basically how you do this. Okay? So that's L equals 2. What about L bigger than 2? Well, we did this for L equals 3. Again, it's not quite as interesting because the 3 graph over FP has a much simpler structure. The required Hilbert class polynomials that show up are for these discriminants here, for this list of discriminant. Happily, they're all still linear or quadratic, so the whole same methodology still works. And then we started looking at L equals 5, and then 2 of the Hilbert class polynomials that show up are like degree 4 polynomials. And yes, I know, and they're also irreducible over the integers. And yes, I know there's like formulas for degree 4 polynomials, and they're solvable and so on, but you know, life is short, right? And again, the case for L odd is really not that interesting, and then if you go bigger, it just gets worse. So I mean, we just sort of, we kind of, so L equals 3 and L equals 2 we thought is like enough. But in principle, you could do this, right? I mean, yeah. Okay. So that's about the spine and the FP graph. And then, because Taha knew a lot of graph theory and sort of knew what was kind of an interesting thing to look at when you look at graphs, he started gathering a whole bunch of statistics. So we have like reams and reams and reams of plots and Excel spreadsheets and so on that have all sorts of data. And I want to share sort of some of the most interesting data with you. Well, let's put it this way. I'll share the data that we can actually either prove something about or maybe at least say something about. So once you know what the spine looks like, it's actually not so difficult to figure out what the diameter of the spine is. Now, what is the diameter of a graph? The diameter graph is like the furthest you can travel from anywhere to anywhere. It's like the longest path, right? It's like maybe you live at the very north end of the city and your friend lives like at the edge of the south end, and so this is like the furthest that you can travel. That's the diameter of a graph. And again, this very much, of course, depends on what the spine looks like. But for the cases p congruent to 1 mod 4 and p congruent to 3 mod 8, the diameter is always really short, right? Because it's maybe like a couple of attached tripods or a couple of attached edges or something. So you can go through these cases and you'll always see that you get values between 1 and 5. Now the p congruent to 7 mod 8 case, Remember, that's the one where the FP graph has these cycles and with edges hanging off of it. So it's much more interesting there. And it's sort of governed by the length of that cycle. And what's the length of that cycle? Well, you can determine that. That's r plus 3 over 2. And what is r? Well, this is again for L equals 2. Conceptually, I guess you could take any L, but for L equals 2, what you do is you two split. So you look at one of the, you look at one of the ideals in your order above 2, and you look at its ideal class, and R is the order of that ideal class. Okay? And in this case, it's easy to prove that the ideal class is actually odd. So R is odd, and so R plus 3 over 2 is an integer. Okay? And again, then we have these two kind of nasty congruence classes where we couldn't resolve anything, and in particular, you can't resolve the diameter, because of course, it makes a big difference whether two of these cycles are somehow attached or not, right? And so we really can't determine the diameter. But what we did do is plot the data. So here, these are, so of course you might have multiple components. So this is just the mean diameter. And this is for L equals 2, and for the first 250 primes congruent to 7 mod 8. That's the interesting case. And you see here, so here, right, I mean, these are the really tiny diameters. I mean, they sort of settle in around whatever, 5 or something like that. But what is this upper thing here? Well, the order of this ideal, right? I mean, if your class group is cyclic, then this ideal might generate it, right? And so this R could be as big as the class number, right? And the class number from the analytic class number formula is roughly the square root of the discriminant, well, absolute value of the discriminant. So it's roughly square root of P. And so R plus 3 over 2 is roughly as big, can be as big as square root of P over 2. And that's exactly this line here. So this curve here, I mean, this is square root of P over 2, okay? So that's the spine diameter. Okay, so that sort of tells you how far you can travel within spine components. And then the other thing that we looked at, and this became actually quite interesting, is the so-called center. So what is the center of a graph? Well, in order to define the center of the graph, you first need to define the radius. So how do you get the radius? So the radius is as follows. You take every single vertex, and for every single vertex, you figure out the longest path to anywhere, okay? So the longest path to anywhere. And then you take the minimum of the lengths of all these longest paths, and that's the radius. And what is the center? The center is the collection of vertices for which the longest path coming out of them is equal to the radius. So you can think of these vertices as somehow being closer and better connected to anything else. So it's like, now you're like in the city center, right? In the city center, you don't have that far to go anywhere to the periphery, right? It's not like visiting, you know, you live in the south and you visit your friend way far in the north. Now you're in the center and you don't have that far to go anywhere in the periphery of the city. So that's the center, right? So this is the center. Center can be thought of as the vertices of being sort of best connected. And initially what we did is we wanted to look at the center of FP, of the FP graph, of the spine actually, because there, right, you have Frobenius, and so every time you have a path, you know, Frobenius gives you a second path. And so we thought, well, maybe these things are somehow better connected or something like that. But it turns out the radius and center data for the FP graph are not so different for the FP bar graph, and so we focused on the FP bar graph, and we plotted this, and we get this very interesting pattern. So this is the size of the center of the graph for L equals 2 for primes from 5 to 20,000. The picture for L equals 3 is quite similar. So we stared at this and basically said, what the heck? I mean, is this like random? You know, what's going on here, right? Yes. And so we were stumped. And then we posted our paper on arXiv. And so here's a lesson. You should always crowdsource your research. Like, you should always post on arXiv, because there's a lot of smart people who look at this and they give you answers. And so we got some really, really good answers for why this behavior is happening. So here's a smaller version of that same picture, but it has some other stuff in it. It has a black line, and it has some green stuff, and it has some red stuff. I hope, can you guys see these colors? Yeah, good. All right. So let me explain what's going on here. So the blue is just the same as before. That's the center data, right? Okay? And the black is also easy. This black line here, this is p over 12. This is the number of vertices in the graph, in the FP bar graph. So no center counts ever go beyond that because that's all the vertices, but you see they go pretty close. The green stuff and the red stuff is the interesting stuff. So let me tell you about the green stuff first, because the green stuff seems to be like very, very close to the actual counts. And this is an idea that we got from Jonathan Love. So thank you, Jonathan Love, for providing this explanation. And he said the following. He told us what you're seeing is actually exactly what you should be seeing if things behave randomly. And what he explained is the following. So you have an integer valued function, right? Where, the center counts. And it has a very slow growing mean, namely the radius, which is roughly log p over 12. And it has a very small standard deviation. And such functions should give exactly the picture that you see in blue. And the green actually models this, and it models this by a Gauss distribution. So what you do is you generate sort of a random graph of the right size, a 3 regular graph, your L equals 2, so the graph is 3 regular. We limited ourselves to p congruent to 1 mod 12, because then neither 0 nor 1728 is supersingular, so it really is honest to goodness 3 regular. Every vertex you assign what's called an out eccentricity, so you assign the length of a longest path randomly. And then you do a discrete Gauss sampling from that. In this case, to fit it the data, the mean was chosen to be roughly 1.8 log p. The standard deviation was 0.38. And then you get exactly those green lines. And now, of course, somehow, random paths, like, for example, paths of adjacent vertices, they're not really independent, so it's not quite right. But still, this seems to be modeling things quite closely. And so this is actually exactly what you should be getting if vertices are sort of, randomly in the center, so to speak, right? So that's the green lines. And the red lines also came from an answer. They're not quite as close, but they still sort of mimic roughly the same, you still have sort of the decreasing thing these steps. And that came from Thomas Dekru and another Jonathan Kamada Erickson. And they said the following: you can try and think of sort of the ideal all the ideal possible ways of having paths of length up to the radius and compare it to the actual number of paths, to the actual center size, and get and model this. And so the way you get these red lines is as follows. So you model all the possible idealized path whose length is the radius, or up to the radius. And you do this as follows. Pick a vertex. That vertex now has L plus 1 neighbors. So you make it the root of a tree, and you make L plus 1 edges down. That's the L plus 1 neighbors. Now, each of these, the next vertices, they all have L neighbors. So now you give it L kids, and L kids, and L kids, and so on, until you're down at the level R, where R is the radius. So you have this tree. It's not hard to count the number of vertices in this tree. This is a simple counting exercise. So the tree somehow models, ideally, every possible way in which you could get from the root vertex to any vertex for a path of length at most R. And you subtract from the number of vertices the actual number of vertices of the graph. And that sort of is a measure of how likely you are to be in the center. And that's what these red curves are, or lines. They're not quite lines, but they're almost lines. Okay, so that's what you get there. And the way to read these blue lines is really the following. So you start, let's say you're somewhere at the top of a wave, and it corresponds to a certain radius value R. And now as p grows, so p is the x-axis, you start adding vertices. So now it gets harder and harder and harder to reach all these vertices within paths of length R, right? And at some point, you've added so many vertices that you really can't reach any more vertices within R. They all require at least R plus 1. Whoop, you jump to the next wave, and you get to the next wave crest. So this is what's happening here, okay? So this is, even though it looked very, very regular, this is exactly, because we thought, well, this isn't regular, this isn't random or whatever. This is actually evidence that the spine behaves quite, and the FP bar graph behave like randomly when it comes to vertices being in the center, okay? So So thank you to these three gentlemen for providing these answers. We also plotted the center data for the FP graph, and they're plotted here. And there's two plots. You see here, first of all, it's the same wave pattern. It's not quite as pronounced as for the FP bar graph, and we thought maybe it's a little bit different, you know, because Frobenius permutes the vertices and keeps the vertices of the spine fixed, and maybe the center behavior should somehow be different, but it doesn't seem to be. And you get the same wave pattern. So this is, again, the size of the center for the FP graph, again, for primes from 5 to 20,000, and for L equals 2, and it's divvied up by congruence classes. So on the left, it's divvied up by congruence classes modulo 3, and on the right by congruence classes modulo 4. And so I hope you can see this. Some are blue and some are red. And what I want to draw your attention to is on the right side, there are a lot more red vertices at the wave crests than blue vertices, especially compared to this here. It's a little bit hard to see maybe, but there's a lot of blue vertices up here, a lot of blue vertices and red vertices here. Here, at some point, the blue vertices stop, and and you only see red vertices at the top. So what we observed is, well, first of all, even when you limit to the FP graph, the center counts spread over the entire range. So they're not somehow smaller or something like that. They still fill out these waves, but you definitely get higher center counts for P congruent to 3 modulo 4. And this is to be expected because, first of all, the radius values are bigger for that case, especially for like 7 mod 8. You also have, connectivity of 1728, which in this case is supersingular plays a role, but this is really, again, exactly as it should be, exactly as you expect. And you see that the wave patterns for the FP graph are very, very similar to the wave patterns of the FP bar graph, even though Frobenius introduces conjugate paths on the FP graph, right? Every time you have a path in the FP graph, it corresponds to a conjugate path, right? So it's really not quite, that's the whole spine thing, right? It's really not quite random, but that doesn't seem to be reflected in these wave patterns. Yeah. So we have lots more plots and pictures and spreadsheets like this. For example, we looked at things like the periphery, so everything that's outside the center. We looked at things like what's outside the spine, which was termed, Taha termed this the abdomen of the graph, which I thought was very apt. We have many other things, but these are sort of the most interesting data that we got and that we really can say something about. So, so I think I will leave it at that.
Thanks a lot for the very visual talk. Are there questions from the audience?
Answers, yeah. Beth.
I was wondering about the L equals 2 case. You have the weird 71 and 119. Is there really no hope of a congruence condition describing what's going on there? Is it just like 120 is not enough? Or is it like something's going on that's just not going to be describable by thinking about
Yeah, that's a good question. I don't know. We haven't really looked at that. I don't know. Sarah, do you have an answer to that or something? We haven't really. I'm not sure. I'm not sure.
Case by case, if you compute the size of the rim.
Yeah, sure. Yeah, so I can repeat that. Of course, for any given instance, you can plot the rim and you can look at how things work, but sort of a general condition, I don't know, P has to be congruent to this modulo 2400 or something. No, I'm not sure. We don't have anything, and I'm not sure if you can get anything, right? Because you don't really know, you don't really know a priori kind of the order of 2 in the class group, and you don't really, yeah. So I have no satisfactory answer for you, I'm afraid.
Other questions? So you mentioned this lower connectivity of 1728. Can that have such a big impact that it's really visual?
No, I don't know. I mean, we also checked how often it's in the center. It doesn't seem to make really that much difference. I think it's really more, I mean, it might contribute, I don't know. I think it's really more due to the higher radius values, really, the different radius values, yeah. So it's just one vertex, right? So.
Yep. Other questions? Yes. Yeah.
So can you explain why 120 is enough? So the mod 8 I see, but why the mod 3 and the mod 5?
It just sort of came out. I mean, one of the Hilbert class polynomials we look at is h minus 15, so there's a 3 and a 5 in there. I don't know, it just sort of came out like this, right? I mean, you just end up putting all these congruence conditions together and from this laundry list of ingredients that I gave, and this is what came out, right? But I think, I mean, it certainly makes sense to have a 5 and a 3 in there from the h minus 15. It certainly makes sense to have a lot of 2s in there, like 8 or so, and I think that's how the 120 comes about, yeah. Oh.
More questions? If not, let's thank Renate again.